Okay, so this is week 12. In this week, we will present some information about the natural convection, heat transfer by natural convection. Before we start this topic, we need to complete the remaining topics or subtopics from last week. So last week we were talking about the internal force convection, and we were up to the heat exchangers, and we said at that time that you will have the experiment or the practical that you had already had on last Friday. It was about heat exchangers. So we will go through this topic, will not take too much time because you already had some good knowledge about it in the practical. But yeah, we'll go through the major formulas. In our analysis, like in any other analysis we did in this unit or in any other units, most likely we start with the steady flow, because this is the easiest. This is the easiest case we start with. So we call it steady flow, and also we say like the specific heat can be treated as constant. So specific heat doesn't change much with the temperature range that we have. And also there is no axial heat conduction. So the axial heat conduction is insignificant. And what I mean by axial heat conduction, if we have, for example, just to make this clear, so we said that if we have a heat exchanger, so double tube like here, heat exchanger. So we have fluid, for example, cold fluid coming from this side. Sorry, hot fluid, say hot fluid, and leaving from the other side. And we have cold fluid coming inside in the tube in the middle. So the heat will be exchanged, be transferred from the hot fluid to the cold fluid. So this is the cold here. All right. So now we assume that all our calculations are about the heat transfer on normal surface, right? So this is our assumption from beginning. If I take this tube, this is the cross section of the tube. We said that heat transfer across the wall. So the area is, or the heat transfer is normal to the area, or the heat transfer area is the area that's normal to the heat transfer direction, right? And in our assumption here, we say axial heat conduction is insignificant. What do we mean by this? There is no heat, like we say that the heat transfer along the tube, for example, heat transfer along the tube to the outer side is negligible compared with the heat normal to the surface. Okay, so this is another assumption that we take in our analysis. And the fourth assumption, the outer surface of the heat exchanger is assumed to be perfectly insulated. So here outside the heat exchanger is insulated. So it means that there is no heat transfer to the ambient from this side. Okay, so there's no heat. This heat is negligible. So all the heat transferred is to the cold fluid. Okay, so these are the four assumptions that we start our analysis in heat exchangers. And then because of this, we can say that the heat transferred or heat received by the cold fluid, or here heat gained by the cold fluid, is equal to, so this is heat gained by cold fluid, is equal to the heat rejected by hot fluid. Okay, so that's these two values are equal. So we can start from this in our analysis. And therefore, if we go to the second, just one point here, in case of, if we have one of the fluids at two-phase, like in two-phase condition or two-phase, we have a two-phase change process, such as condenser or a boiler. So in a condenser, we are condensing steam. So when we condense steam, actually, we said that the amount of heat of evaporation or heat of condensation is equal to the HFG, right? So we can simply find out Q dot by referring to the difference between the enthalpy of saturated fluid or enthalpy of saturated vapor minus enthalpy of saturated fluid, which is HFG. So we just know, we know the HFG from tables multiplied by the mass flow rate of that fluid, then we can get the heat transfer. Okay. All right, if we want to represent this on a chart, so if we say, let's say the y-axis represents T and the x-axis represents the length of the tube. All right, so in this case, we can simply draw the change in temperature for the parallel and counter flow heat exchanger. So we said last time the parallel heat exchanger, when we have both fluids entering from the same side. So for example, here in this figure here, we have both fluids entering from the left side. So the hot fluid from the left and also the cold fluid entering from the left. And then when we show it on the diagrams, both of them starts from the same point, but of course, different temperature, but at the same length, from the same point of the length. So at the beginning of the heat exchanger, we have T cold in and T hot in, and then they exit at the same, at the same point of the length. So T out and T hot out and T cold out, both of them exit from the right side of the heat exchanger. And therefore, we said that to find out the heat transferred, we said we need to refer to the logarithmic mean temperature. And this is like I think you are quite familiar with this. This is the way that we need to find the temperature difference. So in the heat exchanger, no more temperature difference, like the temperature difference that arithmetic mean temperature, which means that we should say T surface minus T fluid, we have to refer to logarithmic mean temperature. So this is how to find out the temperature difference in heat exchangers. So we don't use T, let's say TS minus T fluid. This is not used here. We use the delta TLM, which is the logarithmic mean temperature difference. Okay, so in parallel flow, you always say the left side, which is the hot fluid in, minus the left side of the cold fluid, which is here in this case, cold fluid in. So delta T1 here is delta T hot in minus T cold in. Okay, and delta T out or delta T2 is the difference between the out temperature. So T hot out minus T cold out. So quite simple, very straightforward. So you go to this again, you say delta T, this is delta T1, the difference between these two. And here, delta T2, difference between these two temperatures, T out, hot out minus T cold out. All right. So this is for parallel flow. For counterflow, the method is like, we'll apply the same rule in heat transfer. So again, here heat transfer is T dot is U A delta TLM, logarithmic mean temperature. But here, logarithmic mean temperature, same thing, delta T, we need to use delta T1 and delta T2. But delta T1, we look at it here, look at this figure. Delta T1 is TH in minus TH TC out, right? Because at this side, we don't have in for the cold fluid, we have out. So we say TH in minus T cold out. And the T delta T2, all same thing, we say TH out minus T cold in, all right? So the formula will be the same, but the difference in temperature will, we have to change it. So in this case, we use the same delta Tm formula, but the values of delta T1 and delta T2 is different because the position of the cold fluid temperature in and temperature out is different now. Okay, you just follow this graph and you see that delta T1 is the difference between hot fluid minus cold fluid, hot fluid in minus cold fluid out, and delta T2 is the difference between the hot fluid out minus cold fluid in. Okay, so that's only difference between both cases, between the counterflow and parallel flow. Okay, so we can notice, like, from both, if you compare the counterflow and parallel flow, you will find that delta TLM, delta TLM in counterflow is bigger than delta TLM found in parallel flow. Okay, that's because of this, because we have delta Tm in counterflow is bigger than the parallel flow. What do you expect here? Which one will have more heat transfer? Can someone tell me? Which one will have more heat transfer? If we have delta TLM in counterflow bigger than delta Tm in parallel flow, which heat exchanger have more heat transfer, the parallel or the counterflow? Look at this equation. If I have bigger delta TLM, what should I have? The more delta T, the more Q dot, correct? This means that counterflow heat exchanger perform better than parallel flow heat exchanger. Okay, so as a designer, you should always target, or you should always start with the counterflow design, because this will give you more heat transfer. So the heat transfer efficiency will be better, correct? In this case. So because of delta TLM is higher in counterflow. Okay, so any question? All right, so this is like just in a brief how to find heat transfer in heat exchangers. There are so many other applications you will find in the appendix. So I put it in appendix here, but if we have different type of heat exchangers, because most likely we don't have only one pass, we have multi-pass of heat exchangers, but it's like the time is not in time is not enough for us to complete everything. But if you want to have a look here, there's all these figures shows how to find the correction factor for each one of these heat exchangers. So this is, let's say, for the first one, this is it's a one shell heat exchanger. As you can see, we have the two shell, for example. If you can see here, two shell heat exchanger and so on. So many, actually, so many cases. Also, we have for the cross flow, different design. So we have single pass cross flow with both fluids unmixed. And also we have single pass cross flow with one fluid mixed and the other unmixed. Okay, so that's actually different designs of heat exchanger. So you can go through it if you like and have a look, and if you have any question, you can always come back to me. But these are in the appendix. So what we had in the practical actually was covering this topic. Okay, so any question before we go to the week 12 topic? Okay, no question. Okay, so let's then let's start with heat transfer, natural convection, and radiation. So these are the last two topics that we're going to present today. And next week we will do revision. Actually, next week lecture is quite important, because what I'm going to do is I will do a revision for you for the whole course and present the most important topics that you need to focus on during your revision. So can you prepare yourself very well to the exam? Okay, so please try to come. Everyone should come to next week lecture. It's quite important. All right, so as we said here, this week is about natural convection and radiation heat transfer. So we'll present different mechanism of natural convection and what are the major numbers or major rules, formulas that we're going to use to find out heat transfer by natural convection. And also we'll go quickly through the radiation heat transfer. We talked about radiation before, but we'll just repeat it again and for your knowledge. So that's the content. So the physical mechanism of natural convection. Natural convection or natural heat transfer by convection, by natural convection. The motion that results from the continual replacement, we said before, the natural or the motion of that results from continual replacement of the hot air in the vicinity of, let's say, a hot egg, or for example, we put a hot egg in a room. So the continual replacement of hot air by the colder air in the room is called natural convection. The heat transfer that is enhanced as a result of the natural convection current, we call it natural convection heat transfer. Okay, so it's that, you know, straightforward. And natural natural convection heat transfer has many applications. For example, in buildings or in space heating, if you can see, like in this figure here, we have, let's say, this heater or this fireplace, and this fireplace actually allow the heat, allow this fireplace heat the air entering the or inside the heater or the fireplace. So what's gonna happen here, the hot air will rise up because of the lower density, and because of this movement of the air, there will be replacement by cold air. So the cold air will come and enter the heater to replace the hot air. And by this, we will have a movement of air inside the room. So continuous circulation. So the air will keep circulating inside the room while we are heating or while the heater on. We keep the heater on. We have always circulation of hot air inside the room. So this is what we call heating the space by natural convection. And also we can heat a whole building. For example, in this design of house, if we allow the outside air to enter the room or to enter the space from these, let's say, vents, you know, there's like windows or vents. This will, the cold air here, the air outside will be has less temperature than the inside air. So what's going to happen here, the hot air will rise up and start to leave the house from the top part of the room or the top part of the house. If we allow the air to exit the house from the top, so we have vents at the top, like windows at the top of the house and windows at the lower part of the house or the other side of the house. So we have always circulation. So we allow the cold air or cool air to enter the house, and this air will push, or the hot air will exit the house because of the lower density, or because also if we have wind effect, we'll try to move the hot or the warmer air to the top part of the house and then exit the house from the top windows or upper windows. And we call this, in the design of buildings, they call it passive cooling. So we have passive cooling in summer, if we do the design in this way. And also we have passive heating. Same thing we do. In passive heating, we can actually heat the house by allowing the sun, by like exposing one side of the house. For example, this side here, the wall of this house get heated. So if the house of this, if the wall get heated, if there is space between the wall and the outer air, there is, let's say, a glazed wall between them, so that this glass will not allow the air to go outside. So we can see that the air from inside will come inside this space, get heated, and leave the space or this wall. They call this wall trump wall. They leave the wall from the top part. So by doing this, actually we are heating the house using solar radiation. So using the thermal mass of the wall, so we keep heating the house using this thermal mass, and we call this passive heating. So passive cooling or passive heating. All this type of cooling and heating process depends on the natural convection mechanism. Okay. Any question? Right. So now how to find out the heat transfer by natural convection? We should start from the physical mechanism. So the major number that we're going to rely on, remember before when we had forced convection, whether it's internal or external convection, what was the number we used to identify the type of flow? Do you remember what's the name of the number we use? We used to call it, give it a simple RE, right? So we had real number which identify the type of flow in forced convection. In natural convection, we don't have forced flow, right? So the other number that we're gonna identify this, or we're gonna use it in our calculation, we call it Kirchhoff number. And this is the symbol of the Kirchhoff number. In Kirchhoff number, which is a measure of relative magnitudes of buoyancy force and the opposing viscous force acting on the fluid from the surface. So, for example, if I have this part of fluid and it's a warm fluid, we have two forces acting on this fluid. The buoyancy force trying to push the fluid upward, and we have against this, we have friction force trying to push the fluid downward. And this friction is due to the viscous force between the fluid, or the viscous force acting on the fluid, right? So different type of fluid, of course, we have different viscous force, and different surfaces we can have different friction force. So in this case, if the buoyancy force is greater than the friction, we expect that there will be movement of the fluid upward. Okay, this is what happens actually in natural convection, because we have the buoyancy force of the fluid is higher than the viscous the viscous force or the friction force acting on the fluid. We have movement of fluid to the upper part of the space. Okay, so this relates to the Kirchhoff. We like the Kirchhoff number actually measures this magnitude of buoyancy force. And Kirchhoff number identified by this formula. So this is the formula that we need use to find Kirchhoff number. As you can see, the formula consists of gravity, which is, you know, this is constant gravitational acceleration. And we have the coefficient of volume expansion. This is actually the temperature factor, because, as you know, with a difference in temperature, we have difference in density. And because the density difference will create the movement of the air, we have to include it here. So Ts also temperature of the surface, and T infinity is the temperature of fluid far from the surface. And also we need to know the length of the surface. So this is, let's say, the length here. This is what's the length of the surface. So length of the geometry, and then of course we need to know what type of fluid we are dealing with. And this can be represented by the kinematic viscosity. So because each fluid has different kinematic viscosity. So if we know the temperature or T film, we can go to tables and find out the gravimetric viscosity of that fluid, and we can substitute it in this equation. All right. So this is the Grashof number that we need to use from now on in natural convection. We don't use Reynolds number, we use Grashof number. Just please remember. Okay. Any question? Please ask if you have any question. Okay. So now we come to the empirical correlation, because remember before, let's say in forced convection, when we found the Reynolds number, we use this Reynolds number to find out Nissot number, correct? And we said that in natural convection there is no Reynolds number, there is Grashof number. So now we're going to use the Grashof number to find Nissot number in natural convection. So what's the formula for this? As you can see, in terms of heat transfer coefficient and thermal conductivity, it'd be the same formula. There's no change. So Nissot number is equal to H multiplied by L, the length of the object or the surface, divided by the thermal conductivity of the fluid. Now, to find the value of N and U, we can always refer to this rule. As you can see, either we use this or the second one. So it has constants. It has C as a constant, and it has N as a constant. And these constants are given in tables. So I'll show you very soon. Based on the Grashof number, once we find the Grashof number, we can go to tables. So once I find the Grashof number, I can go to tables and find what are the values of C and N to substitute them in this equation. Okay, so also it appears in this formula another number, non-dimensional number, RA. And RA also only in natural convection. RA is they call it Rayleigh number. It's also a non-dimensional unit, non-dimensional number, which is the product of, as you can see, product of Grashof number and Brandon number. So you multiply Grashof by Brandon number, you get Rayleigh number. So either you use Grashof number multiplied by Brandon, or you use RA if it's RA available. So any one of them will be fine. So use this part of the formula or use this part, doesn't matter. Any one of them will be fine as long as you have the values. Okay, so now, as we said, the Rayleigh number is multiplication of Grashof number and Brandon number. Okay, and because Grashof number is represented by this formula, we've done this before, previous slide. So this is the Grashof number formula. We multiplied by the Brandon number, then to get the Rayleigh number. Now, why we need this? Because the tables that we're going to use, the tables that we're going to use to find Nissot number, some of them requires Rayleigh number, not the Grashof number. So if this is the case, then you need to find Rayleigh number. If the table refer to Grashof number, then of course simply just use the Grashof number, right? So now if we want to find heat transfer by convection, natural convection, then we should follow this equation, of course, the Newton's law of cooling. Now, the only problem comes when we want to find H, because H is found from Nusselt number. So remember, H is equal to, based on Nusselt number formula, is equal to Nusselt number multiplied by K divided by the length of the surface. All right, so now we need to find Nusselt number to substitute it in this formula. And Nusselt number, of course, as we said, we need to go to tables to find it for natural convection. Okay, so to do this, we refer to table 14.1. So we will provide this table in the formula sheet. But if you don't have the formula sheet or you want to use the book, that's fine. But as I told you before, it's really good idea before you enter or you come to the final exam. It's good to print all these formula sheets and tables, print them, put them next to you. It's really easier for you to search the information while they are printed. If you put it on, like, leave it on the desktop with the exam paper and with the questions, you may get confused and then you may maybe do mistakes when you select the value. But if it's on your it's on your desk, you can highlight it by your pen and you can get the correct values from the tables and from the graphs. Okay, so try to do this, please, and just to prepare yourself before the exam. By the way, the quiz, I already sent you an announcement yesterday about the quiz 3. I have postponed it to next week because some students ask for further time because you have many submissions this week with the lab and other units quizzes. So kind of, try to help you to perform better in the quiz. We will do it next week. But next week quiz will be written. So it's not multiple choice like the quiz 1 and quiz 2. It's written quiz. Something similar to the final exam. Just want you to practice the mode, the exam mode, written mode. So you write your solution on a paper and then scan it with your mobile phone and then send it to your email to upload it to Views. Okay, yes?
Is 15 minutes enough for this quiz?
We will give you 20 minutes. Yeah, I'll give you more time.
Thank you so much.
Don't worry about the time. That's
how
fine.
many questions over there?
It's only also one question, same as the previous quizzes. It's one question with many requirements, let's say 5 requirements. And same maybe same time, requires same time, but it's written. The reason why, as I told you, because we want you to practice the written exam before the final. At least you know how to do it, like to submit your scanned paper to Views. So you have some practice before the final exam. And also Dr. Ahmed will show you tomorrow or next week how to do this, how to scan it again. Like if you don't know how to scan it, tell you how to scan it and how to upload it to Views, to the right page. Okay. And also I sent you the topics that will be covered by, or you need to revise before the quiz. The quiz also holds 5% weight. So same as the previous ones. Okay. Any question? All right. So now go back to the table 14.1. Now this is the empirical correlations for the Nusselt number for natural convection over surfaces. And as you can see, the range identified by the Rayleigh number, not real number, as we did before, like in forced convection, we are using RA, not RE. Rayleigh number in natural convection. And based on this number, you choose the range. If the range of RE in this, between this value, then you choose this formula. If it's in this range, then you use second one. For entire range, like if you don't want to follow the Rayleigh number, you can use this formula. It's quite complicated, but it also will give you correctness of number. But like in final exam, probably I don't recommend you to do this because it's as you can see, it has mathematical process, and they probably do some mistakes with the power and these brackets and divisions. So if you refer to the first two one to be more convenient for you, but you need to find first the Rayleigh number in order to choose which one is correct. So this is, let's say, if you have vertical plate, you do this. If you have, let's say, inclined plate, you do the same thing, but you need to introduce the cosine theta in the equations. And if you have horizontal surface, whether it's upward, facing upward or facing downward, in this case, same thing, you follow this range of RA. So for each RA range, we have different formula to use for Nusselt number. Okay, so this is the table 14.1. There are other shapes like for natural convection. When we have vertical cylinder or horizontal cylinder or sphere, each one of them has its own formula. So most of them follows one formula, as you can see. Yep. Any question? So probably we have time. Yeah, we still have time. We will we'll try to solve this problem. We'll use Kahoot for this problem, or part of the problem we'll use the Kahoot. So the first requirement. So we have three cases actually in this problem. This is natural convection problem, and we have given the dimension of the plate. So the plate, as you can see, the height 0.6, the width 0.6, so it's like square plate. And this plate at temperature 90 Celsius, as you can see, the plate is hot. We put this plate in a room. The room temperature is 30 Celsius. So if you put hot surface inside inside warm air, let's say the air here, the air temperature is lower than the surface temperature, what do we expect? Heat transfer from the plate to the room, or vice versa, from the room to the plate? What's the direction of the heat transfer here? Can someone tell me, please? Bakhtiar? Bakhtiar? Tariq? Tariq?
Yes, sir.
So from what you can see here, like for the first case, we have the heat transfer direction from which side to which side?
The heat coming in and then it goes out. So basically,
sorry. Yeah. So the heat will be from the surface to the room to the air, or vice versa, from the room to the surface.
from surface to the air.
Correct. Why?
because the heat difference between the air and the surface.
Yeah, but the major reason is the surface temperature is higher than room temperature. Correct? We said that
Yeah, that's what I meant. Yep.
heat transfer always from high to low temperature. And that's why the heat will be from the surface. So Q dot will be from the surface. Yeah. Okay. So this is the case that we're gonna work on in Kahoot. So what we need to find, actually, we need to determine the heat rate, or determine the rate of heat transfer from the plate by natural convection. So of course, if we expose this plate to the room air, there will be heat transfer by natural convection. The hot air will rise up, the cold air will replace the hot air, and so on. This kind of circulation, we call it natural convection. So we need to find the rate of heat transfer by natural convection when we have the plate vertical position. And then after that, we will compare it with when we put the plate in facing up, horizontal but facing up. And then the last case, when we put the plate horizontal, but the hot surface is downward, as you can see. Okay, so we have three cases. We need to see which one of them will give us highest heat transfer rate. Okay, as a designer, if you want, let's say, to design a cooling system, natural cooling system for a certain device. For example, you have electronic component. For example, electronic components, IC, you want to call the IC. You need to find out which way you need to put the plate, the plate that cools, or the fin. We call it fin last time, remember? So we need to find out how to put the fins. Is it put it in this way, vertical side, horizontal side, but upward, or horizontal side and downward? We need to see which one of them will give us more heat transfer, because the more heat transfer we have, the more cooling to the component. So if let's say, for example, if I put the electric component somewhere here, this is my electric component, or if I put it in this way, in this position, or should I put it here? This will depend on the value of heat transfer I get, heat transfer rate. So if I find that one of them has the maximum or higher than the others, then I choose that design, because this design will give me more cooling. So the more cooling is better for us. So the component will not fail because of the increase in temperature. Right? Any question before we move? So this is we're gonna take the first case now. We'll go to Kahoot and solve this case, and then go back and do the other cases and compare between them. Any question before we move to the Kahoot? Right. All right, so let's Okay, here we go. This is the number. Okay. So we have we have Tengshi, Abdulaziz, May,
Yes, sir.
okay, Bakhtiar, Mervin,
I'm here.
William.
Yes, sir.
So how many students we have now? So only 6 in the class. Where is Elias? Elias. Tariq,
Yes, so I'm joining now.
please join. Tariq. Are you there, Tariq? If you're not joining the Kahoot, well, I'll put you absent. So please join now. Please remember the final exam. You have to you have your camera on and mic on. So try to find for yourself a proper space. And of course, you need to use your laptop. You can use your mobile phone in final exam. It's gonna be messy really. So don't do this, please. Try to organize a space and with your laptop or your PC and with camera on and mic on.
Sir,
Okay. So Elias, are you there? So Elias in.
sir, it will be through the Zoom meeting or
Yes, yes. We'll send you the link before the exam. We'll put it in views. So put a clear message in views that where to choose where to go to the final exam section.
Okay, clear. Thank you.
Yep. Okay. Tariq, oh, you're not there, Tariq? We're gonna start.
Yeah, I'm coming, sir.
Yeah, please join now.
Sorry for making you wait.
Okay. Okay, good. So now let's start. I really, if you can, please, can you get a paper, a pen and a paper, just to write the values of each question so that you can use it in the next question, because sometimes you need to use the value from previous step. So please try to prepare a pen and a paper to write down the result for each section. Okay, so let's start. So now we need to find T film. What's the film temperature? Remember, film temperature is surface temperature plus fluid temperature divided by 2. Correct, everyone done it correctly. Thank you. That's good. Good result. Okay, you are very close to each other. So let's do the second one. Then we're going to use this film temperature to find Rayleigh number. So first of all, remember Rayleigh number formula. This is the formula for Rayleigh number. Right, so I showed you actually the result when yeah, that's good. But just to show you, this is the right number. So how to do it? So this is the correct answer. So for Rayleigh number, let me make this smaller. Yeah, so that's Rayleigh number. We need to have the gravity, which is 9.81, multiplied by beta. Beta is 1 over the temperature. So we have the film temperature, as you can see. So, but it should be, this must be in Kelvin. Just remember 1 over T film must be in Kelvin. So here, T is 60 Celsius plus 273. We'll have 333 Kelvin. Okay, so that's beta. And then, as you can see, TS, surface temperature, which is 90, and the fluid temperature or the air temperature is 30. All right. And if you look here, they put K. Actually, this is not. This is the shouldn't be K. Should be Celsius. This is from the book, because even if you let's say the difference between temperature doesn't matter if it's Celsius or Kelvin, because difference will give you the same value, same result. So, but here the values are in Celsius. So the difference between them, 90 minus 30, then multiply by L, the length of the plate, which is 0.6 to the power 3, divided by kinematic viscosity. Okay, so kinematic viscosity is already given in the question, but in the exam, you may need to go to table A22. All right. So from table A22 at T film 60, you can find all these values. You can find the K, the Prandtl number, the kinematic viscosity. These 3 values you need it in your calculation, so you have to find it. All right. So that's one. The first requirement in the question. Just before we go to the second one, because in the second one we need to find Nusselt number. So based on this value of Rayleigh number, we're going to go to tables and find the value of Nusselt number. So please write down this value now on the paper. Did you write this, everyone?
I'm nearly there, sir. Just like,
Yeah, write down this value, please.
Yeah, I wrote it, sir.
Okay. So now this value based on this value, we're going to go to this table. So I will keep this table on this page and try to find which case you're going to use from the table. So first of all, what's your geometry? Is your plate vertical or horizontal? Which one are we going to use from these? Are we going to use the vertical plate, inclined plate, or horizontal plate? Which one of these we're going to use? Based on the question that we have.
Vertical.
Yeah, vertical. So the first one. So based on this, please check. This is the Rayleigh number column. Which one of range? Which range are we in? Just check, please. Are we in this range or in this range of Rayleigh number based on the one that you wrote down, the one that you had on your paper? So what's the number we had? What was Rayleigh number? Can someone give it to me?
Times 10 to the power of 8.
Sorry, 6. What was the Rayleigh number from previous step?
7.656 times 10 to the power of 8.
Yeah. To power 8, right?
Yeah.
Yeah. So if I want to choose, it will be in this range, right? Because 10 to power 8 is 10 to power 9. Correct? Are you following me?
Yeah.
So if it's in this range, then we can use this formula for Nusselt number. Okay, so write down this formula, please. Write down this formula, so you're going to use it in the second question in Kahoot, third question in Kahoot. Write down this formula, please. Everyone, did you write it down?
So what's that number above the L in the?
L to power quarter, so 1/4.
Okay, all right. Thank you.
Yeah. So LRA, so RAL, it's RA. There's no L. It's RA to the power 0.25 or to the power 1/4. So RAL is Rayleigh number. Okay, so that's that one. So now we go to our question and try to continue. Okay, so next one, we're gonna find Nusselt number. Okay. So Rayleigh number is given. You're gonna go tables, we found it from tables, Nusselt number. Now need to find it, the value, what's the value? Okay, that's right. So in this range between 94 to 114, I think it's 113.4. Okay, good. All right, so now we know that we found the Nusselt number. Now from Nusselt number, we need to find the heat transfer coefficient. Okay, so based on the definition of heat transfer coefficient, you know the definition of heat transfer coefficient, Nu is equal to H times L divided by K. Okay, so we have the values, all the values are there. We need to find H. So from this equation, we can find H because now we know what's Nusselt number. All right, so please write down the Nusselt number from previous step, the correct number. And then we're gonna find H from here, right? Okay, so we'll go to the next question. What is H if Nusselt number is 13.4? So again, Nusselt number. So already given K is given here. Good. Okay, so we have 6 of the, you got the same correct answer. Good. All right. So the last one is to find the heat transfer. So now if we know the heat, we know the H value, and we know the area. So A, the surface area actually is the square area multiplied by T surface minus T fluid. So all of these values are already known. You can find Q dot easily. Okay, so now the next step is to find Q dot. All right. What is the rate of heat transfer? H already given. Okay. Are you referring to the lecture notes in views to get these values? Or you are doing this by yourself now? Because your answer is quite quick. Yeah. Anyway, as long as you understand the process of calculation, that's fine for me for the time being. If you get it from the materials, from the notes, or from your own calculation, that's fine. But I need you to understand really how to do it, how to find these values. Okay, good. So we can have the result now. The Aziz number 3. Number 2 is William. Number 1, Tarek. Okay, thank you. Thanks everyone. Thanks for your contribution. Okay. Let's go back to the example. So we done the first case here in this example. So we as we said before, you need to find the film temperature. Everyone knows how to find film temperature now. So once you know the film temperature, you can go to tables, table A22, because now we have air. So this for air, we can get the values for K, Rayleigh number, kinematic viscosity. All right. And in the Khrushchev number equation, we need also beta, which is 1 over T film in Kelvin. So we find it already found this. Now you need just to follow this formula, substitute the values in this formula, and we get the Rayleigh number. Now we said from this, you can use this Rayleigh number, and we go to tables. The table, either we use the table or use this formula to find Nusselt number. So as you said, as I said before, this formula is really quite complicated. If you want to use it, that's fine. If you can do it, use this to give you an accurate value. Otherwise, you can go to the table that we mentioned before. You can use this table. For this case that we have now, in this range, I can use this formula to find Nusselt number, all right? Or otherwise, just follow whatever in the example here, follow this formula to find Nusselt number value. And we found it here is 113.4. So we're gonna use this formula to find H value. Okay, so once we found Nusselt number, we can find H value. So for this case, H is equal to 5.306. Now the area, the heat transfer area, we said the surface area of the square. So we know this side of the square is 0.6. So 0.6 square give me the area of the plate. Okay. Now we have the area of the plate. We have the heat transfer coefficient, the area already given, the temperature, surface and air temperature, both of them are given. So just simply substitute the values and we get the heat transfer rate. So this is for the first case. Okay, so just remember the first case, we put it down on the paper. The first case give us 115 watts. Let's compare this case with the horizontal case. We said we're going to compare between 3 cases and see which one is the best in heat transfer. Okay, so the first one, the vertical one, gave us 115 watt. Let's see what the other cases that we're going to have. When we have horizontal and the hot surface upward, this is TS, 90 degree, facing upward. Okay, so in this case, we do the same thing. We need to find Rayleigh number. So Rayleigh number, we follow the same equation that we did before. And we found that Rayleigh number is, the range of Rayleigh number is this, 1.196, 10 to power 7. Again, if I go to the tables, I'll find this in the range of the first formula. Yeah, because the first formula, the range is 10 to power 9. This is 10 to power 7. So I'll get the same formula for the vertical case. Or as we said, you can put it in, you look at here, this is what we found from the table, from the table that we had. So as you can see here, Nusselt number is 31.76. Okay. Now from this Nusselt number, I can find H. But you can tell now that Nusselt number here is less than previous case. This gives me an indication that I'm gonna have less H. If I have less H or less heat transfer coefficient, means I will have less heat transfer, because heat transfer coefficients is multiplied by the other variables in the equation, or other factors in the equation. So if I have more H, I will have more heat transfer. So let's see what's the heat transfer we'll get here. This is the heat transfer. I have the heat transfer coefficient is 5.9, which is Nusselt number here, we have decay, because for the air, the same thing. We have the only thing here, the only difference with the LC. Okay, and as you can see here, LC different from L here. All right, and that's give us, give us H 5.9. Now, if I use the area, the same area we had before, now substitute these values. Substitute these values, as you can see here, H multiplied by A, S multiplied by delta T. This will give me 128. So the first case was 115. The second one, 128. All right. The last one, when we have the surface downward. So TS here is downward. Okay. So we do the same thing. We apply the same formulas. Now, natural convection is to be determined from this equation, or we can go to tables. Remember the table that if you have the range of RAL, and we can find the range of, or the equation for Nusselt number. Okay. And from this equation, we can find Nusselt number again, 15.86, much lower than the previous case. Now from this, we can find H using the same formula, because H is equal to K multiplied by Nusselt divided by LC. All right, and then we'll find that H is equal to 2.97. Okay, so substituting this value in this equation, we will get Q dot is equal to 64.2. So now we have the vertical one. $115 watt. The horizontal one facing upward, the heat transfer rate was 128 watt. And the horizontal one, but facing downward, the heat transfer is 64. So the best design we can use is this one, facing up, horizontal, but facing up. will give us more Q dot. Okay, that's the design that we need to select. Okay, as you can see, all of them use the same procedure, the same formulas. The most important thing, you need to find the Rayleigh number, and then from Rayleigh number you can find out Nusselt number, and then H, and then Q dot. Okay. Let me check what's the time now. Yep. Okay. All right, so by this we finished the heat transfer by natural convection. So the last topic in this course is radiation heat transfer. And I think we mentioned this before. We talked about radiation in week 7. We gave you some hints about heat transfer by radiation following the Stephen Boltzmann formula. But just to let you know that heat transfer by radiation, or recall this again, that the heat transfer by radiation is due to electromagnetic waves. And because of electromagnetic waves, heat transfer by radiation can exist in vacuum as well. So we don't need medium to do the transfer, like we don't need solid or fluid. It can travel in vacuum. Okay. And we mentioned before that for each, maybe we didn't mention this, but just to let you know that electromagnetic waves of different wavelengths differ significantly in their behavior. Depends on the wavelength of the radiation. But the visible spectrum, let's say the visible wavelength, the infrared radiation that we use, let's say from the sun, it falls in this range, as you can see in the figure. So this is actually this is the range of visible radiation or visible spectrum. And most of our work in thermal system use this range of wavelengths, because we are dealing with infrared and or visible spectrum rays. Okay, but again, we don't have to go into details. The only thing that you need to know is the Kirchhoff's law of radiation that we mentioned before. So in Kirchhoff's law of radiation, the emissivity and absorptivity of a surface at a given temperature and wavelengths are equal. So the amount of radiation observed by a surface is equal to the amount of radiation emitted by the surface. Okay, so we'll give it this as epsilon emissivity E, and this one is absorptivity alpha. So both of them are equal. So if at a given temperature and wavelength, they are equal. And when a surface is completely enclosed by a much bigger surface, for example, if I put a plate, hot plate inside a room, big room. So this is hot plate inside a room. The surface, so then the amount of heat released from this plate will follow Kirchhoff's law if we know the surface emissivity. Okay, so we need to know the surface emissivity and the surface area, and also we need to know the temperature of the surface. So this is Ts, surface of the temperature of the surface, and also temperature of the surroundings, T surroundings, right? So if I know all this information, then based on Kirchhoff's law of radiation, the net rate of radiation heat transfer between this surface and the surrounding or the room can follow this formula. So you know this formula now. This is for radiation. So we know the Q dot by radiation. We know the emissivity of the surface, and the emissivity of the surface depends actually on the type of the surface, the roughness, and as well as the color of the surface. So we said the color is quite important to find emissivity, and sigma is we said Stephen Boltzmann, sigma is Stephen Boltzmann constant, and AS is the surface area, Ts, the surface temperature, but should be in Kelvin. So be careful, please. When you substitute the value of radiation in this equation, it must be in Kelvin. Otherwise, you'll get wrong answer. Okay. So as you can see here from table 9.6, for each material, you have different emissivity. So if you, let's say, if we want to have high radiation from the surface, which material we can use? For example, if I need more radiation, should I use the red brick, or should I use, let's say, aluminum foil? If I want to get higher radiation, so for high Q dot by radiation, which one should I use? Red brick or aluminum foil? Which one has more emissivity?
Red brick.
Red brick, correct. So the more emissivity value, I'll get higher Q radiation, because as you can see here, emissivity multiplied by the other factors. So for less emissivity mean less Q dot. So I should I have to get higher emissivity material in order to get more heat transfer by radiation. So I can choose the red brick because give me the emissivity value is higher than the other, than the aluminum foil. Okay. Okay, so that's actually in, this is the end of heat transfer topics that you need to prepare yourself for the final exam. Other appendix, I put some other information here if you like to go through it later on to increase your knowledge in this area. It has different explanation about the natural convection. How did we develop the equations of natural convection? And but again, it's up to you. If you want to do it, if you want to go through it to increase your knowledge, that's fine. So, and also it has some information about natural convection from fin surfaces. You remember before we talked about fins in conduction, heat transfer by conduction, and we studied at that time the heat transfer or the heat transfer inside the fin. Now we study, because these fins actually most of them used for natural convection. Some of them used for force. As you see in the, let's say we mentioned this before, in your computer, in your laptop, there is a fan, and the fan actually blowing air over this fin. So this will increase the heat transfer. But in some cases, they don't put fan, they just rely on natural convection. So you don't have to put fan. If the area of the fin is big enough, then the natural convection or heat transfer by natural convection will be enough to cool the device underneath. Okay, so it depends on the design. But for natural convection, as you can see here, we have the case that the fin case, how to find out heat transfer from the fin using natural convection. Right. So it's we are up to here now. If you have any question, please ask now. Next week, as I said, I will go through the topics in thermodynamics and also the topics in heat transfer, and I will highlight the major formulas that you need to focus on so that you'll perform better in the exam. As I said, the exam will be open book, but you need to write your calculation on a paper and then scan the paper and submit it to views. So we will practice this kind of exam next week in the quiz. And the quiz basically will be on heat transfer by, like, you need to study or you need to revise the heat transfer by conduction and forced convection. Natural convection is not covered. You need to only to focus on heat transfer by conduction and convection. Okay, so just try to go through the formulas that we use in each case, and also the tables that we use. Try to practice the examples that we explain in the lecture or in the tutorial. So at least you can. It's the question is quite simple. It's not hard, as long as I said, as long as you know how to use the formulas. If you know how to use the formulas, where to use it, then you will be fine. I'll give you just like, quickly. Probably it's a good idea to give you a quick process in this kind of examples. First of all, you need to ask yourself, when you have a question, heat transfer, first of all, you ask yourself, what type of heat transfer? Is it by conduction? Is it by convection? Or by radiation? This is the first question you ask yourself. Okay, if it's conduction, then it's quite simple. Correct? because in convection, you say we can, okay, convection, it's follow this equation, Ka delta T by delta X. We said delta X is thickness, delta T is temperature difference. K is thermal conductivity, and A is the area of the surface area. Okay, normal to the heat transfer. This is straightforward. And then the other option here, we said that, remember, we said delta T divided by R. And because if we have multi-layers, then we need to find R total, correct? So if we have, let's say, thermal resistance 1, resistance 2, resistance 3, so I have R1, R2, and R3. I need to add them together to get R total. So this is my R total. I substitute this in this equation to get Q dot. All right, so that's maybe the easiest part of the heat transfer. The only thing you need to do here is to find out the R, thermal resistance of each layer of the material. In heat transfer convection, maybe this is the most like complicated part by convection. So convection has two parts. You need to ask yourself, if it's convection, you know that this convection, you need to ask yourself, is it forced or it's natural? All right. And if it's forced, then ask yourself again, is it internal or external? Okay. And then the other question, when you have internal or external, what type of turbulent, laminar, or turbulent? Because that will depend on the type of flow will affect the equation that you're going to use from tables. Same thing for external. Is it laminar or turbulent? And then from that, you can go to tables and find out the right formula to use. For natural convection, it's actually, we don't have cases, only you need to find RAL, Rayleigh number, and from Rayleigh number, you can find the equation. Okay. And the last one, which is radiation. Radiation, actually, we're going to take the simple form of radiation, which we mentioned now, radiation between a surface and the surroundings. And in this case, we just follow the Kirchhoff's law of of heat transfer. In this case, it's a Q dot. We said Q dot is emissivity multiplied by sigma, Stevens-Boltzmann, multiplied by the area, multiplied by surface to power 4, and the ambient or surroundings to power 4 in Kelvin. Okay, so that's just a summary how to approach your solution. Before you start your solution, you need to ask yourself these questions. And once you identify the case, then you can choose the proper formula, or you can choose the proper table for it. Okay. Any question, guys?
So what's the other one besides laminar?
Yeah, the laminar and turbulent.
Oh, turbulent. Okay.
Yeah. So these are two, laminar or turbulent. Yeah. Of course, in the force, remember in internal, we have other two cases. I don't want to do it too complicated now, but the two cases are whether it is constant temperature, constant TS, or constant heat flux. This is another option, because you remember with constant surface temperature, we have to use the delta TLM, logarithmic mean temperature difference. And we said this is the case when we use it for in heat exchangers. We have constant surface temperature, while constant heat flux, we use just delta T, just arithmetic difference. Okay. Okay, guys. Any question? Other question? I will go through these formulas again next week, and then I will highlight, as I said, I highlight the most important cases that you need to focus on. But again, if anything not mentioned in next week lecture, you can always refer to the materials, because I said it's open book exam. You can refer to the formula sheet, or you can refer to the slides, lecture slides.
Sir,
Yes.
what are the lectures and tutorials that cover on the quiz 3?
Yeah, quiz 3, I said it's you need to go through the conduction and the convection, forced convection, sorry, natural convection. This week lecture is not covered. So only forced convection and conduction.
Okay, thank you so much.
Okay. Any other question before we leave today?
So,
Yes.
question about the lab report.
Yes.
So if I don't have enough for 2000 words, do I lose mark?
Not really, no. As long as you you do it properly and the similarity is not high. So, but you have to cover, let's say you have to answer all the questions and do the, like, you know, the report in the required template. So let's say you have to do the description of the device, and then the requirement, and then sample of calculations, the results, then discussion and conclusion. So if you follow this procedure, then you should be fine. My recommendation, you can go to views, or sorry, to the learning guide. Let me just try to find out if I can. So if we go to views, let me open views better. Okay, now if you go to learning guide here. Okay, so in the learning guide, you will have the criteria, marking criteria for each assessment. So for example, for This quiz. This is the tutorial. Yeah, these are the practical reports. This is the marking criteria for the report. So now, for example, the major criteria is you must attend the 2 practical, as we said before, and submit the report. Now, if you want to achieve high distinction in the report, you should you should do these things. Okay, so read these to target or to get the high distinction. If you are, let's say, only doing this with minor mistakes, you get this range of mark. So my recommendation is you need better to focus on the high distinction requirements. For example, you put the concept, the ideas, the theories, you explain them in the report, then do the numerical calculation and the theoretical analysis, do it correctly. Then you need to show the results, the table of results or the data collected. And then you put the structure in a logical way, the structure of the report, logical way. And also then you do your comment or conclusion correctly on the results. Okay, so that's to achieve the high distinction mark in the report. Is that clear, Jensi? Yeah.
So do I need to put handwritten calculation on there as well?
It's good if you give a sample of calculation. You don't have to do like the calculation. You put the for every single, because sometimes if you use, for example, Excel sheet, it will do it for you. So if you just put one sample of calculation, and
Yes, I'm using Excel sheet, so I don't.
Yeah, you can put the Excel sheet then.
Yeah, sure, of course, I will put that.
You just print the Excel sheet and put it in the report. That's fine.
In a Word document? Okay, all good.
Yeah, just copy pasted in a Word document and should be fine. But you need to put first, like you put the formulas that you have used in the Excel sheet, put it in separately in the report, and then put the result used by, like, shown by the Excel sheet. And then, yeah, you can just comment on the data or results. Yeah, any other questions?
Can we use the pictures from the lab notes?
Sorry?
Can we use the pictures from the lab notes?
Pictures?
Yeah.
Yeah, no problem.
All right, sure. Thanks.
Yeah, that's fine. And also you have some, I think, pictures in the views. And if you go to the lab, I believe it's shown here. No, yeah, it's the practicals. Yeah, you have lab notes. And also you have, you have the videos, sorry, here the videos, you can watch the videos again. And also you have the instruction here, lab instruction, so you can use them, yeah. Yeah. Okay. And in the, for the final exam, we will put the link at the first page. So when you open this unit page, the first page of the unit, you will find like this, a link. Oh, sorry, I'm not sharing the screen, right? So you'll have, let's say, most likely this kind of link. So a final exam Zoom link. So once you open the unit, you'll find this message. So you just click on this and you'll enter the final exam page. And we'll give you later on the page that you need to open to find your exam paper. Okay, it will be given, it will be active some in exam week. Any other question? Okay.